Record. Good afternoon, everybody. It is October 10th, and it is 1:02. We may begin. Today's class may be a little bit shorter. Miss Alicia, I have sent you an email regarding getting you into WhatsApp. For now, we will stick to the today. We will be expanding on last week when we talked about geometry. We reviewed trapezoids. And we reviewed how triangles interact with most shapes. And we mostly stopped there with what concepts we were talking about. Does anybody have any questions or concerns regarding last week's topic? Do you not understand anything, etc.? Very well. May anyone tell me what the area of a triangle is?
Half base times height.
Thank you, Mr. Nathan. And does anybody remember the area of a trapezoid or have it in their notes? If not, very well. We reviewed last time that the area of a trapezoid is half height times 2 bases of base 1 plus base 2. Okay. So in the trapezoid that we reviewed last week, in the height of the trapezoid, where you have 2 bases, base 1 and base 2, and it comes to this equation for the area of a trapezoid. Furthermore, we reviewed when we compared these two equations, the trapezoid and the triangle, we saw that if either the base or the height of a triangle is 0, the area of the triangle then becomes 0 as well as if the height of a trapezoid were to become 0, the trapezoid would then have an area of 0 because it would be squished into a little line segment like this. However, when we looked and we saw that if we made one base 0, so this base, for instance, if we made our base 0, then it would turn into a triangle. As we can compare our equations, we substitute in 0 for one of the bases, the area equation becomes a triangle. As you can compare here. Now, Does anybody remember the area of a rectangle?
The area of the rectangle equals length times width.
Length times width. So we'll write rectangle here. Very good. So our area is length times width. We can draw our rectangle so that we have length and we have width. As we observed last class, we could derive the area of the trapezoid as dividing the trapezoid into a rectangle and a triangle. So in our model, our trapezoid could be divided up. Base 1, base 2. So that our trapezoid comprised of a rectangle and a triangle. That means our area would have been our height times, in this case, base 1, because the bottom would be base 1 as well, plus the area of a triangle, which is 1/2 height times, this segment would be base 2 minus base 1. And we simplified this equation and it came out to the area of a trapezoid. Any questions so far?
No, sir.
No, sir.
Very good. See. So the way that we were able to determine the area of the trapezoid and how if the trapezoid had one base being 0, it becomes the triangle area, is by analyzing the formula So we experimented with our formula a little and we said that if we are adding these two terms, one of these terms can be 0 and the area will not be 0. And that is how we found out that the trapezoid equation is simply a triangle equation, but with the tip chopped off. At least that's how sort of I described it. Expanding on this concept, I want to look at the triangle area. The triangle area is 1/2 base times height. So can somebody tell us a random base and a random height? Just pop out two numbers.
7 and 14.
7 and 14. Let's say our base is 7 and our height is 14. This means that if our base is 7 and our height is 14, then it is true that the area will be. Can somebody solve the area, please?
Sir, the area would be 4 to 9.
Very good. area would be 49. We did this by putting our base and our height into the equation. So what we are saying here is that because the area of a triangle is 1/2 base times height, if a triangle has a base of 7 or a height of 14, then that means this must be true. So let's say that this is our height. Let's measure it across. And let's say that this is a base of 7. And we'll say that this is a base of 7 as well. Can anybody tell me? Do these have different areas? Why or why not? Can I have Mr. Nathan? Would you say that this area and this area are equal?
Yes, sir.
Okay, can you say why or why not?
Because the base is a rectangle and the height is both a triangle. Only on area 2, the triangle is a right angle triangle.
Okay, I see what you mean, Mr. Nathan. Your answer was yes. Mr. Nathan, I'm asking you. Your answer was yes.
Yes, sir.
Okay. So Mr. Nathan, I believe you said that the first area was a rectangle and the second area was a right triangle. So what I think you're saying is that you can cut this triangle as so. So this is the height. And what you did was that you took this side of the triangle, this half, and you flipped it over so that it came over like this and it made a rectangle. And the rectangle is, the area of a rectangle is base times height, but the base that we're using is equal to half the original base. So because of this, the area is 1/2 base times height. And on this side, we know that the area of the right triangle is 1/2 base times height. And as we have, our equations are the same, so the area is the same. At least that's what I'm supposing you said. This is true. While this is true, this is not the actual reasoning behind why the areas are equal. It is merely a demonstration arithmetically. But I do commend you, Mr. Nathan, on recognizing this. Thank you very much. What I would like you to see in our model is that the areas are the same because for two simple reasons. One, we said that our heights are the same and our bases are the same as we drew them. So because the heights are the same and the bases are the same, and there are no other variables in the triangle area, then that means the areas must be the same. Any questions so far?
No, sir.
Very good.
Excuse me, sir.
Yes, miss.
did not get to hear you properly because the rain is falling very hard here.
Okay. So first off, you should make sure your volume is raised up as high as possible. But very well. Continuing on with this idea, I would like to do this again. So let's keep our bases the same, and let's keep our height the same. I would like to ask you now, is the area of this triangle equal to the area of all of these triangles combined? May I ask Mr. Deochand?
I don't think so.
Very well. Can you please tell us why or why not?
The two rectangles are the same, but the far shape, it has like one triangle that has like 180 degrees, and there are multiple triangles on the other side. They're like 100 each, so that could be too much.
All right. I like the justification. I would like to point out that these are not rectangles. If I'm interpreting what you're saying correctly, these are merely ways of showing measurement. So these are like brackets. They're showing that this is the length of this, or unless you're talking about the rectangles that they fit in. Either way, so Mr. Deochan has pointed out that in one triangle, you have, no, not that. In one triangle, you have 180 degrees. And in these multiple triangles we have here, we can count one, since these two are right next to each other. This counts as 2, 3, and 4. So there are 4 triangles here. So that means that there will be 4 times as much angle. So 4 times 180 is 720. So in this model, there are 720 degrees as opposed to in this model, where it's only 180 degrees. I will get back to this in a quick second. Now, what we can see here is that if we don't know if the areas are equal, we should find out. What we can see in this triangle is that we know how to find the area. It is simply the area equation because it's one triangle. Area equals 1/2 height times base. As we see here, because it has this height and this base. I'm going to make the room here. Now, there's not much that we know about these triangles here. Can anybody tell me what we do know about these triangles?
They all have a right angle.
This is true. So each of these triangles have a right angle. And as such, because they have a right angle, that means the horizontal and the vertical are perpendicular to each other. So that means each of these lines is the height. It's close, but not quite what I'm getting at. How about Mrs. Ariel? What do we know about these triangles?
Sir, they're all equal?
Not quite, because these triangles are really thin, while this one is just a little bigger. But you're very close. In our model, these lines show that every triangle within the that touches the lines as these do have the same height. So what we're getting at is that each of these triangles all have the same height. Let's keep that in mind. So if the height of the first triangle is height 1, then that means the height of all the second triangles is the same as height 1. And because these are all triangles, we know that the area will be all the areas of these triangles combined. Does that make sense?
Yes, sir.
Okay, so we have 4 triangles here. What we know is that for all the triangles, they each have the same height. And they share the height with this triangle as well, because that's what our model says. What we don't know about these triangles is what the bases are. So because there are 4 triangles, there are 4 bases, of which we don't know. However, let's look at our model again. Our model not only says that all the heights are the same, but that the base of this triangle is the same as the bases of all of these triangles added up. Does that make sense?
Yes, sir.
Okay,
Yes.
good. That is why we drew our model this way, because this indicates that the base of this triangle is the same as the base of all of these triangles added up. So the way we write that is, in our example, we use bases 1 through 4. It would be base 1 plus base 2 plus base 3 plus base 4 equals the total base. Does that make sense?
Yes, sir.
Yes, sir.
Very good. So let's try and find our area equation of the 4 triangles. Because there are 4 triangles, we will be using 4 equations at the same time. But since they're all triangles, we know that they all have the area of 1/2 height times whichever base they have. So let's write it as 1/2 height times base 1 plus 1/2 height times base 2 plus 1/2 height times base 3 plus 1/2 height times base 4. Does everybody see this all right?
Kinda, sir.
All right, I'm perfectly fine. Little space. So the total area of the four triangles, area 2, equals 1/2 height times base 1. Okay. Now we have this long equation of the areas of these four triangles, but it's very long and inefficient the way we wrote it. So what we want to do is try and simplify what we have written here. Can anybody tell me what all four of these areas have in common? Can I get Mr. Aryan?
I don't know, sir.
Okay, Mr. Aryan. When you look at the equation, all the areas, you have 1/2 times height times base 1 plus 1/2 times height times base 2 plus 1/2 times height times base 3 plus 1/2 times height times base 4. What did I say in all four times that I said it that were the same?
1/2
height.
and height.
Very good. Okay, so 1/2 in height is the same in all four of these. So we may simplify this. So then instead of saying that, we can say 1/2 times height times base 1 plus base 2 plus base 3 plus base 4. And this is equal to what we just wrote before. Any questions so far?
No, sir.
No, sir.
No, sir.
Very good. So this is the area of all the triangles on the right side. So can we simplify this any further? Do we know about anything in this equation that we wrote somewhere else? Mr. Nathan, can we simplify this any further?
No, sir.
We don't know anything else? So we have
No,
our height.
sir.
Okay. So Mr. Nathan, we have our 1/2, we have our height, and we have base 1 plus base 2 plus base 3 plus base 4. Did we write anywhere else any information that can help us out?
I don't think so, sir.
All right. Mr. Nathan, what does it say up here?
Base 1 plus base 2 plus base 3 plus base 4
Equals,
and equals B. Base
yes.
and
And base describes the base of this triangle and the sum of all of these bases. Thank you, Mr. Nathan.
Okay, sir.
So with this information, I'll make some room here. We don't know what each of these bases are, but what we do know is that the bases all add up to the total base, what we said from this model. So we can rewrite this equation as area 2 equals 1/2 times height times base. So are the areas the same? Anyone?
I think yes, sir.
Very good, Miss Ariel. When we found the area of all these triangles together and we simplified it down, we found that the height are all the same and the total base of all the triangles added up together is equal to the same base as the original triangle. Therefore, the areas are the same. Any questions?
No, sir.
Very good. We can demonstrate this by looking at a different model. I guess I didn't need to give these numbers. Let's have a triangle here. Here is our base. Let's say that base is 7, and let's say this height is also, no, let's say this height was 14. We have a triangle of this base and this height. So what is the, we know that the area is 49. Aside from finding the height in base and plugging it into the area equation as we did, what we can do is that we can say, instead of the area of the triangle being comprised of the one whole triangle, we can say that if we were to cut this in half along the height as we drew it down the middle, we have one triangle of height. And because we drew it in half, we have half the base. And then we have another triangle of height and half the base. So this would be half the base. There we go. So as we drew it in this area equation, we did A equals 1/2 times 7 times 14. In this equation, I'm going to switch these around just so it can look simpler. In this equation, we simply plugged in the base and the height as we had it into the area equation, and we had our area 49. How can we do the area of these two triangles? I'm breaking up a bit.
Sir, after you find the area of the whole triangle, you can divide it by half again.
Okay, so you are saying that the area we can cut in half and we can say that's the area of each triangle. Very good. Inversely, because we said that we can cut the area in half to find the area of the triangles, we can also see that the area of each triangle must be equal to half of the area of the total triangle. That's what it means to cut it in half. So in other words, what we did is that we took the area equations of both of these triangles, area 1, which is equal to 1/2 height times the first base, plus the area of triangle 2, which is 1/2 height times base 2. And we can plug in our equations. We can plug in our numbers as we have them, and we will come out to the same area. This example here of the 4 triangles that we drew in are essentially the same concept. The only difference is that we cannot pick up the triangles and rearrange them like jigsaw pieces to create the original triangle. But using our equations, we can see that the area of these 4 triangles is the same as the area of the whole triangle. Similarly to this model, if we were to have a triangle where one part where we cut off the height was bigger than the other part, we would have to do the actual math by understanding what base 1 and then base 2 would have been to find the area of the whole triangle. But the main idea is that because our triangle equation is area of 1/2 base times height, if you have multiple triangles of the same height, you can combine them into one bigger base, which may be equal to the base of one bigger triangle, so that the areas are the same. Any questions?
No, sir.
No, sir.
Very good. So let's take this one step further. Let's say that we had 2 triangles which we could not directly find the equal bases for. So let's say we had one long right triangle and one, this would be like an acute triangle, or an obtuse triangle. We said that we knew the base and height of this right triangle because it's a right triangle. And we knew that the height of both these triangles are the same. Now all we would need is to have the base of this triangle. So let's say this is base 1 and base 2. Because they have the same height, but it has different bases, what we can do to find the area of both of these triangles together is by writing the area as 1/2 base times height, because that's the area of a triangle. So we know that it's the same height. So height In this triangle's case, it is base 1. And in this triangle's case, we know that the area of this triangle is 1/2 height times base 2. Because we can see that each area equation contains 1/2 in height, we can simplify the equation into 1/2 height times base 1 plus base 2. And that is, if you recognize it, the area of a trapezoid. So take these two triangles together and you can get a trapezoid. Does that make sense?
Yes,
Yes.
sir.
Okay.
I don't really understand.
I'm sorry?
I don't really understand it.
Misunderstood. Okay. So what we were saying before is that we can take two triangles and put their areas together, and the area would be the area of a triangle with the same height with just a bigger base. That's what we said in our example beforehand. We have one big triangle and two little triangles with the same height, and the bases add up to the base of the bigger triangle. Now, what happens if we have two triangles where, in this instance, we can have the triangle, we can write the triangle this way, so that's upside down. We can say the area of both of these triangles is 1/2 base times height, where in this example, we gave the height to be the same, but it has two different bases. If we were to find the area total of both of these triangles, we can have the area of the first triangle and the area of the second triangle. And if we add them together, it has this equation, which is what we used to find the areas and say they were equal last time. However, this time, instead of fully simplifying it and saying that base 1 and base 2 are the bases of one larger triangle, we can see that when you add the bases 1 and 2 together as they are, that they have the same area as if you were to use a trapezoid equation. So this is an example of how you can combine two triangles together to create a trapezoid. The reasoning behind this would be if you had two triangles which were equal, let's say two right triangles which were equal, they had equal height and equal base, then what you can do is that since the area is 1/2 base times height, you can just add both of them together and you would get a square. This would be if you took this and you flipped it over and you stuck it on this side so that you had not necessarily a square, but it would be a rectangle of, not that one, of height and base. If you were to have another example where the base and height were different, well, the base would be different. If you had another example like this, where the base is different, what you can do is say, well, if the bases are different, but the height isn't, and you were to add the areas together, it would come out to be a trapezoid. Does that make a little more sense?
Yes, sir. Understand.
Okay. The point of this is not to say that this is how trapezoids are constructed, but this is a way of showing that two triangles can be combined to make a trapezoid, and that is a way that trapezoid is derived from triangle. Okay, 148. Now before, I believe it was Mr. Deochand who pointed out that even though they had the same base and the same height, they had profoundly different sums of angles. So we had one triangle and then four triangles. Pretend that these bases are touching. So that, well, this triangle, this is technically one whole triangle because their heights are pressed against each other. This would have a total angle of 180 degrees, and this would have a total angle of 3 times 180, which is 540 degrees. So this would look more like this. So even though the bases and the heights are the same as we drew them in the model, they have a lot different total angles. Angles do not necessarily area is independent from angles. That's what I'm trying to say. So, for example, even if you had a square and a hexagon, even though the hexagon has a lot bigger angle total, that doesn't mean that the square with 360 degrees total doesn't have the same area as the hexagon. What matters is the length of the sides, because that is how we determined area. If we have 1/2 base times height, we have the sides of base and the sides of height, and these determine our area. What we just reviewed is that if the triangles have the same base and height, then they have the same area. That is the same as saying that this triangle and this triangle will have the same area if they have the same height and base. What the total angle means, however, is something different. Because if you were to have a square and a hexagon, for instance, and they had the same total area, how could they be different? Mr. Aryan, if you had a hexagon and a square that had the same area, how could they be different? What are the two measurements that we make of shapes? We have area and something else.
Perimeter.
Perimeter, exactly. So if two shapes have the same area, if they are different shapes, then that means they must have different perimeters. Okay. That's what it means to be different shapes. So what we can note is that, yikes. So why can't I draw a triangle today? Goodness. So what we can say later on is that even though the area of the total area of all the triangles together is the same as the one bigger triangle, with the total degrees being far more than the degrees of this triangle, this will have a much larger area, a much larger perimeter. This will be important to understand later, because you'll be working with saying that certain shapes are the same as other shapes, but because other shapes will have different surface area or a different perimeter, they act in a different way than other shapes do. It's difficult to explain at the moment, but when you guys are all in trigonometry and you do more complicated shapes, it'll make a little bit more sense then. But here's what we can show, that because we said that this was equal to this in area, we can just keep adding more triangles forever as long as their bases all equal this and they all have the same height. So that means that this triangle and these triangles all have the same area as if we were to say that this is like a bunch of triangles. So, Mr. Deo-chan, before we said that the base and height, if the total bases and the heights are equal, then that means that the areas will be equal, correct?
I think so, sir.
Yes, because we said that because these triangles have the same height as this one and all of their bases added up to be the same as this base, they have the same area, correct?
Correct.
Okay. So if this were a bunch of triangles and they all had the same height, but all their bases added up to be the same base as these, wouldn't that mean that all of these triangles have the same area as well? Mr. Deo-chan, yes or no?
Yes, sir.
Very good. So long as all of the bases of, let's say that this is tons of triangles, so long as all of their bases add up to be one base, that means that, and they all have the same heights, then that means that the total area of all these triangles together will equal the area of this. But what we can see is that because there are so many more shapes in this than in this, and it has so many more sides, we can see that the perimeter, when we said that it describes how long it is when you move around the object, we can see that because there are so many more sides, that you're traveling a lot more in this shape, in all of these shapes than here. So if you were to walk around the sides of all of these shapes, it would take a lot longer to walk all these shapes than this one. Does that make sense to everyone? Does anybody not understand or has questions?
No, sir.
Goodness. Can you all hear me well? Am I breaking up?
No, sir, I can hear you.
Okay,
Sorry, you are breaking up a little bit.
okay. So because it is 2 o'clock now, let's take a step back and take a 5-minute break or so. Does that sound good?
Yes, sir.
Okay, we'll take a break until 2:06.
Okay, sir.
Okay, is everyone there?
Yes, sir.
Okay, good. So what we were just talking about was we related the area equation of triangles to describe how multiple shapes can be added up together and have the same area, but how they have really different perimeter. This is really important for examples like in real life when you're building things. When you're building things, oftentimes what happens is that when you order material, you'll get it in shapes. So let's say you ordered a ton of steel, it would come out into a bar or like a really long grate or something of the kind. This would just be in raw material. So oftentimes what people do is that they break apart the material into little pieces. So oftentimes what you do is that you break up material into pieces, and let's say it was one square that was this big, but you cut it up into little bits like this, it would still be the same area. But oftentimes what engineers have to do. Yes, Miss Alicia?
Nothing, sir.
Okay. So oftentimes what engineers have to do is that they have to take the material they're given and they have to map out how they use their material. So they have to see, let's say you wanted to make, I don't know, you wanted to make like a bar, like a toy. You want to make a bar like this so kids can take these bars and they can stack them on each other and play with them however they want to. But you were not given a bar when you ordered the material required to make it. You were given, let's say, just a square. And you had to turn the square into a bar. What you would have to do is that you would have to map out the length and the width, or in this case, the length and the height, to find out how much area of material you will need from this square. Can somebody give two numbers, please?
10 and 5.
10 and 5. So the height of our block is 5, and the base of our block is 5. So this would mean that the block has an area of 50. And the square would have also an area of 50. So an area of 50, let's say that our block was, it's a square, so that means that it would have to be square root. So 5 root 2 and 5 root 2. So what we saw is that if we wanted to make a block of height 10 and width 5, we would need to order a square of length 5 root 2 and of course 5 root 2 height. That's how much we need to make this. Furthermore, if we wanted to make more complicated structures, let's say we wanted to make a maze, and each of the maze, and the maze was made up of little squares of 1 square meter. So a square is equal to 1 square meter. Let's say this was the start and this is the finish. How would we find the area of this whole maze? How about Ms. Alicia? Ms. Alicia, if we know that all the squares are 1 meter squared, how would we find the area of this maze?
Sir, I don't know.
Okay, well, we know what 1 square is, right?
Sir,
So if we know what 1 square is, could we count all the squares in the maze?
yes, sir.
Okay, so if we know the number of squares in this maze and we know how much the area of each square is, could we then find the total area of the maze?
Yes, sir.
Very good. So that is how you would find the area of the maze. And subsequently, whatever the area comes out to be, or let's say instead of question mark n. So if the area comes out to be n, however much the area is, then that means the length and the width of the square we have to order with is the square root of n. Any questions?
No, sir.
Okay. So this essentially describes what we were doing. We were taking, we took one big shape, the triangle, to use this example one more time. And we said that from the material that this triangle makes up, we could make it into these shapes. So we use the same amount of material to make these shapes, but because the shapes are shaped in the way that they are, they take up, they have a lot bigger perimeter because you made them into different shapes. you can make an example out of this with any of your household materials. And what you can think of is, in order to make this shape, whoever designed it, the engineer or whoever, if they had to make this maze, they had to count up the area of the whole, for this example, maze. And they had to say, this is how much area, this is how much material I need to make up this maze. So they had to order the amount of material that it was given in. Does that make sense, everyone?
Yes, sir.
Okay. So I would like for all of you guys, this will be your homework. You guys have to pick anything in your house, it doesn't matter what it is, and draw it as a shape. So if I had my pencil here, you don't have to do the whole three-dimensional pencil. You can just say that the pencil is a rectangle with a triangle on top. So let's write it down. I want you to use any shape, use any object. Draw it as a shape. I want you to take your shape. Let's have our pencil here. And I want you to say that the shape has whatever measurements you need to find its area. So you can choose whatever you want, as long as it's not all ones or something like that. So let's say our pencil had a height of 5, the height of this triangle on top was 1, and the height of this rectangle is 4. You can say that the base of this pencil has a length of 1, and so does this triangle. So you can use whatever measurements you want on this shape to say that the amount of area it takes up is a certain amount. So let's move that over here. So I want you to find its area. Then lastly, what I want you to do with the area is, with that, I want you to say how many triangles are you going to need? So in this example, I'm going to give you a triangle of base 1 and height, no, not base 1, base 4 and height 7. And what you're going to tell me is how many triangles are you going to need to build the shape that you chose. And I'm going to put in the WhatsApp chat these directions again, but in a more easy to understand way. Does that make sense to everybody?
Yes, sir.
Yes.
Sorry, sir. Can you please repeat it back for me? You're breaking up a little.
That's fine. So I want you to find any object around your house and draw it as a shape. Then I want you to say what the area of the shape is and draw your measurements of that shape. And whatever area you get, I want you to say, for that area, how many triangles of this dimensions do you need to build your shape? Does that make sense, Mr. Deochand?
Yes, sir, I understand now.
Okay, I'll be putting these directions in the WhatsApp.
Sir, when we draw our shape, do we have to measure the actual length and width of the shape, or can we just make up a random number?
You can make up whatever numbers you want, as long as they're not all ones and you don't. I want you to put at least a little effort into it, but you are allowed to measure it if you'd like. The point of this activity is that it doesn't have to be hard. You can do it easy if you want to, and I don't care necessarily if you get it wrong. I would just like you to challenge yourself if you'd like to and show that you understand the concepts.
Okay, sir.
Sir, when we finish doing this homework, it will be due the next Saturday of our class?
Yes.
Okay, sir.
So, sir will be going over it next Saturday.
Yes.
Okay.
Sounds good, everyone?
Yes, sir.
Yes, sir.
Okay. Before we move on, does anybody have any other questions about something that I didn't explain as well as I could?
Sir, for the homework you said find as many triangles in the shape that we choose. What if the shape we chose can't have triangles in it?
So you're gonna have to say of this triangle, which I'll send in the WhatsApp. You will have a triangle of base 4 and a height of 7, and you will have to say how many of these triangles do you need to come up with the amount of area you need to build your shape. Does that make sense?
Yes, sir. So whatever shape we choose, we have to do the area of the triangle base 4, height 7, and figure out how many triangles we'll need for our shape. Okay, sir, I understand.
Yes. So it's like if so it's like I have this eraser. There's a certain amount of material in this eraser. If you had to order material in these blocks, I would be asking how many of these blocks do you need to make up this eraser? That's what the homework essentially is. Okay, unless there are any more questions, we can move on and talk about something a lot less complicated. Can somebody tell me what a shape is? Just things about a shape that are important.
Sir, all the sides are equal of the shape?
I think you're thinking of a regular shape. I mean just any shape in general.
Sir, it's important for the shape to have lines.
In a sense.
A shape can be in 2D, 2-dimension or 3-dimension.
Now you're getting somewhere. So when we have a shape, it can have flat sides. Most shapes can. But a circle is also a shape. And a circle doesn't have flat sides. There are two things specifically that describe what a shape is. I'll leave that. A shape is, as Mr. Nathan has told us, a shape is flat. And by flat, we mean 2D. When Mr. Nathan said 3D, that refers to a form. A form is 3D. That refers to things that actually exist in real life. So for instance, a pencil and a marker and such, they have form, which means they have volume. They are not flat. A shape is flat because if I were to pick this triangle up out of the screen, it would be like paper. So if I were to have this and I turned it to the side, you wouldn't be able to see the side because it has no depth. But because the shapes are flat, they are two-dimensional, and forms are three-dimensional. But we will not be talking about three-dimensional forms for now. We will be talking about one-dimensional. Does anybody know what one-dimensional is?
No, sir.
No,
Okay.
sir.
So if we don't know what one-dimensional is, can somebody say what is two-dimensional?
Sir, I think I know what is a one-dimensional.
Okay, what is one-dimensional?
It's like a plane shape.
You're very close. A plane describes, it's an infinitely long shape. So it would be like this whiteboard. If this whiteboard went on forever into the ceiling, into the sides, this way, so up and to the right and to the left and down forever, but it never went, it never had any depth, so it never went towards you. That's what a plane is. So a plane is a shape that goes on forever. You're very close.
Sir, one-dimensional shapes are measured in one direction.
Very good, Mr. Nathan. So when we talked about area before, area is two-dimensional. If we have a square, the square's area is equal to length times width, or because it's a square, it's just length times length. As we've said before in this class, if we were to say that the length of the square is 1 centimeter, then that means it would be 1 centimeter times 1 centimeter. So the area is 1 centimeter squared. So if the centimeter is squared, that means that is referring to an area. But if it was just 1 centimeter and it was just centimeter to the power 1, that would refer to the line we multiplied by to find the shape. Because it was length times length, it was this line times this line. And since this squared represents the 2 in two-dimensional, that means the power to the 1 for just 1 centimeter means that one-dimensional describes a line. Any questions?
No, sir.
No,
So one-dimensional describes a line. So lines are extremely simple because if you have a line that breaks off like this, it's no longer really a line. It's more of like an incomplete shape. Because the line, as Mr. Nathan has said, it can only point in one direction. If we look at the definition, it says that that it points in one direction. Now let's think about that. We have one direction which describes 1D, and we have points. Does anybody know what a point is? What is a point in math?
Sorry, showing in decimal.
Very good. So whenever you say like a decimal, you say 1 point something like that, 1.2 pi is 3.14. The point refers to the decimal, and the decimal is called a point because it is just a dot. And in math, we call a dot a point. A point has nothing to do with decimals. It's just called that because it's a dot that we point there. Now, a point in math is literally just one spot in space. So it would be like saying it is this this point right here. It is not this point to the right or to the left or to the up and down. It is just that spot in space. You don't need to worry about it right now, but a point is actually zero-dimensional. The reason why is because if we see our definition, one direction, the D refers to dimension, or in other words, direction. A point doesn't have direction. That is why it is zero-dimensional. A point doesn't point towards anywhere. It's just where it is. A line does point in a direction, because if I had a line and we drew it on a graph, we would say that the line does have direction, and that direction would be the slope. What points are useful for is that you use points to build up everything. So if any of you have ever seen like atoms or molecules and stuff like that, everything is built up of little circles. Like let's say this ruler. You have this ruler which is built up of a lot of little dots, and these are atoms. If you apply this to shapes and to lines, you say that a line.
Sir,
Yes?
sir, my battery is very low right now.
Very good.
Sir, will this video, will it be on YouTube?
Yes, I am uploading all the recordings of these classes on YouTube from now on, and I sent this in the WhatsApp group. So if you go to that YouTube channel, the recording of this lesson will be there soon.
Okay, sir, my battery is very low. I will put it to charge and I will check YouTube to see the video.
Thank you, Miss Ariel. Have a good weekend.
You too, sir.
So if we apply this to a line, we say that a line is made up of a bunch of points. Yes?
By the way, what is your channel's name?
Miss Alicia, I'll have to get with you about you joining WhatsApp, but at the end of the class, I'll say the channel. Good. When you apply this up to lines, you say that a line is a bunch of dots in a row. So the dots point in one direction. So when we say something points, we literally deconstruct the word points, and it's literally multiple points. So if you have 2 points in space and you draw a line between them, because there are 2 points, then that means that direction refers to where one point is in respect to another. Are there any questions?
No, sir.
Okay, so now you know what the word points actually means, literally. So this is what a line is built up of. It's made up of points. If you were to look at it another way, you have your number line. Start with 0, 1, 2, 3, so forth. What these niches describe here is that they're showing where the points in on the line are that the number is at. So at this point in the line is 0, at this point is 1, at this point is 2, at this point is 3, and so forth. So in that sense, if we go back further to what we said, if we just say that the answer to a problem, if it asks how long is a yardstick, you cannot just say 3, because 3 doesn't have any meaning. What we would say is that a yard, well, you guys have meters. So if we had a meter stick, we couldn't just say that the how long is the meter stick? The meter stick is 100. We have to say that the meter stick is 100 centimeters. And what we were doing when we say 100 centimeters is that we are saying centimeters describes a line, and the line is the length of the quantity of 100 centimeters. So numbers are a point. They do not describe a direction. And that's why you can't measure things in terms of numbers alone. You have to say a number of lengths, which would be centimeters. So a number of centimeters, 100 centimeters, is equal to 1 meter. Continuing on with this idea, or moving on from this idea, there are only 3 things you need to know about lines. There are 3 types of lines. There is a line, there is a ray, and there is a line segment. Have you guys used these before? I'll take that as a no. This is all you need to know about lines. This is a line, a ray, and a line segment. As you can see, what are the only differences in these lines that you can see? May I get, how about Mr. Aryan? What are the only differences in these lines that you can see? If not Mr. Aryan, Mrs. Anusha?
Sorry, breaking up a bit.
Ms. Anusha, these are the only 3 types of lines there are. It's a line, a ray, and a line segment. Can you see from what's drawn here, what are the only differences between these lines?
Sir, they go in different directions.
Kinda. The point is that some of them have arrows and some of them have dots on their ends, correct?
Yes, sir.
Okay, good. So that's what we're getting at. You can see these arrows and these dots. And as Miss Anusha correctly pointed out, these also describe directions. It is implied when you have an arrow that because the arrow points in a direction, that the line points in that direction infinitely. So because there's a line, that means if a line has two arrows on the side of it, this is what we generally refer to as a line. It just goes on for forever. A ray, if you can see, has an arrow, so we know it points in this direction forever, but it has a dot on the end. And this dot is a point. What this is saying is that the ray ends at this point or begins. So if you ever looked at like a timeline for history, you would say that history started at 0 AD, because that's how we measure our years. And we say that this was 2,000 years ago. So our modern timeline goes to now, which is 2000 AD. We can say that this is where this timeline of modern history begins at 0 AD, and this is where it is now. Now, we know that time goes on for forever. As far as we're aware of, there will not be an end of time. So that means this timeline will continue to grow forever. So it'll point in this direction. And we say that somewhere along here is 4000 AD, for example. And you guys understand what I'm talking about. But what differentiates a ray from a line is that it begins somewhere. In this case, it would be the beginning of modern history. A line segment, as you can see, has 2 points on the ends. That means it has a beginning and it has an end. So this is something temporary. Let's say with time again, let's say that this line describes the year 2000. So in the timeline of the year 2000, it starts at the year 2000 and it ends at the year 2009 in December. So this starts in January and this starts in December. So a line segment is specifically described to be temporary. So it has a beginning and an end. A ray has a beginning, but it has no end. And a line has no beginning and has no end. If we go back further into earlier topics, we talked about the real number system. Does anybody have any questions so far? Okay. If you remember, we talked about the real number system. I believe it was with you guys. I said that natural numbers or integers. Does anybody remember what integers describe? Mr. Nathan, do you remember what integers are?
Sorry, sir, I couldn't hear.
Okay, it seems everybody's breaking up. I'll tell you what, we can stop class right now since a lot of people are having internet connection issues. And today class will be ending a little bit shorter than usual. Does anybody, so we'll stop right here. Does anybody have any more questions they'd like to go over? Okay. So if there are no more questions, we can stop class around now because we went over plenty today. All right. It seems a lot of you are having connection issues, so have a good weekend. Okay, Miss Anusha, Mr. Aryan, Mr. Deo-chan, and Mr. Nathan. We are ending class a little earlier. Okay, Mr. Nathan, Mr. Deo-chan. Okay.
Okay, sir. Bye.
See you, Mr. Deo-chan. All of you have a great weekend.
You too, sir.
You too, sir.